we left off talking about this really interesting problem, and it was so rushed. I feel terrible that it was so rushed. Let's look at it. It was the one about if somebody told you that they tested positive for the AIDS virus and you didn't know anything about their behavior, nothing, this is all you knew about them. And it was a test that was just extremely reliable. I'm trying to look for this test here. Here it is. We never finished this problem. Okay, so I'm talking about page 114. And I said this test was very reliable test. And let's just check it out. 99% of the time, this is a real test, Alyssa, that was done for years. 99% chance that if you actually have the virus, you will test positive, okay? Correctly give you a positive result. But also, if you don't have the AIDS virus, there's still a 6% chance that you'll incorrectly get a positive result called a false positive. 99% chance, though, if you have it, if you have AIDS, 99% chance that you will get a positive. All right, so then the question, this is the key piece of information right here, that, and this is all true data from a few years ago, that about 1% of the blood samples that Alyssa was testing were truly contaminated with AIDS. All right? Now people look at this, and we asked, and last time I asked you, and I said, okay, knowing all this information, what do you think? Somebody isn't a good friend of yours, you don't know what risk behavior they have. They say, hey, listen, I just tested positive for AIDS. Am I in trouble? What do you think? Do you think it's going to be really likely that I have AIDS? And you look at this, and the person tells you, if I have AIDS, they tell me 99% of the time I'm going to test positive. And then they say, there's only a 6% chance, when I don't have AIDS, that I'd get this positive. If I have the positive, there's a 99% chance. And then I'm also told it's really rare. Why me? 1 out of 1,000, 1 out of 100, get this. So you say to him what? Oh, don't worry. Get retested. Very unlikely you'd have AIDS. Or would you say to him, like almost everybody in the class thought, oh boy, sorry to hear this, but 99% chance, I'd say there's probably a 90-something chance you do have it. There's good treatment for it. Don't freak out. Go back to the doctors, etc. But then we saw, when we actually did this intuitively, remember we did this intuitively? We didn't fill out this chart. We just said, wait a sec. We can just do this in our heads. We can just do this in our heads. Pretend there's just 100 of us in the class. And I said, you guys, 100 of us. Let's just think about it. And that's where we came up with this. We said, suppose there's 100 people. Now, out of the 100 people we're using this, only one has AIDS. And I volunteered, if you recall, to be that one person just for a graphic illustration, just to relieve you. I really don't have AIDS. I think some of you were wondering. Somebody even emailed me saying, are you okay? So I don't want to worry you. I might not be okay, but I don't have AIDS. Okay? Could have other problems, but I don't have AIDS. Okay. So, but I'm pretending for the sake of this, that it's me, that I have AIDS. So and you said, and you all agreed, well, 99% chance that a positive person's that if you have AIDS, you're gonna test positive. So you all said, yep, there's one positive. But then I said, well, all the rest of you, if you're like the general public that line up to take blood, that 99%, the rest of you, don't have any AIDS in your blood. But does that mean you're all going to get negatives just because no. That's what that 6% false positive means. It means that even though 99 of you don't have any AIDS, mistakenly, the test is still going to give you a positive result by mistake. And this happens with a lot of tests. So now if you think about it this way, there are 7 people total who have AIDS, who test positive. The question says, what's the chance someone has AIDS given they tested positive? There's 7 positives. That's all you know about the person. But really, there's only a 1 out of 7 chance that that person has AIDS. And so what I'm saying is that this is a very counterintuitive problem. What makes it really counterintuitive is that we're trying to, is this 1% here. We somehow, if there was a 50 chance, if 50 had AIDS and 50 didn't, just think about it. It would be completely different. It would be just how your intuition says. You don't have to write this down, but just pretend if it was 50 AIDS. It's the 1% that makes it really anti-intuitive, because you think of a 50-50 split. So let's say it was 50 AIDS, 50 don't. Well, now, of these 50 people, 99% would test positive. So we could say 49.5 would test positive. Let's just write it positive. And of these 50 that don't, how many would test positive? 6% of 50, 6% of 100 is 6. 6 out of 100 is the same as 3 out of 50, right? So 3 would test positive. So now we'd add these together, and instead of having 7, we'd have how many positives? We'd have what? 52.5 positives. And how many of them would really have AIDS? How many of them would really have AIDS? Hello? 50 of them. So it would be just how you thought. It would just be, overwhelmingly in the high 90s positive. Just your intuition. Just as your intuition tells you. And what's very hard for people to do is to not imagine that it's 50-50. We always imagine things like, imagine that it's really only, in this case, and with many diseases, it's not 50% of the population, it's only a small percentage. And that's what we have to, that's why it changes everything. Okay? So that's what I tried to do with your homework. That you had due, where you had to fill out the tables, and I think it's still open by accident. It's not closed till tonight, by the way. Did you realize that? That homework is still open. So, where I asked you to look at questions like this. This question right here about percent, jurors make their right decision about guilt and innocent 95% of the time. So right away you think, that means 95% of the time, 5% of the time they're wrong. They're wrong, and they put innocent people in jail, and they let guilty people walk. That's what we focus on. And we forget this probability, a prior probability of how many are guilty. We have to combine 2 probabilities, and that changes everything. And that makes it not 5% are put in jail and not 5% walk, but a much different ratio here. Okay? Not 5% of the guilty walk and not 5% of the innocent are put in jail. But then on your homework, I wanted to show you that. I don't know if you noticed it, but on the very next problem, I changed that 80% to 50%. And if you do that, make this 50-50, then it's exactly as you think. Exactly as you think. Then yes, this 95% of the time is what is intuitively, it's not only intuitively the clue, but it's also, your intuition agrees with the right answer. So you think, 95%, 5% wrong, 5% of the people are put in jail, and the 5% of the guilty are left free, 5% of the innocent are locked up, okay? And then it would work out that way. Now, I don't know what the true percentages are, but I just want you to understand that what seems intuitive to you often depends on you thinking there's this 50-50 split out there when there really isn't most of the time. Certainly not with diseases, okay? So now let's finish up this table. We can do this table more exactly if you want. we did it intuitively, we'll come up with pretty much the same answer. So we can do that. So let's see. First, I didn't give you a total here. I'm going to give you a total. I usually give you 100, and that would give what? If there's 100 here, we'd focus, and where would we fill in here? What do we know? 1% are truly contaminated. So I could put a 1 here. Correct? And then what would go here? 99. And the next thing I know is that there's a 99% chance that Alyssa will correctly give a positive result. So I'd say 0.99 of the 1, don't close your parentheses yet. This is fine. You'd get 0.99 and 0.01, and you could do your problem. No, it would be fine. But many of you have told me when I did it this way in the past, former students said, please don't do it with fractions. And with decimals. Make these work out to actually a whole person and not 0.99th of a person. You know, I assumed it was a whole person, we rounded up. But if we wanted to do it exactly, is it okay? Should I do that? Make it whole numbers? Then I would just give you, would end up being I'll just move the decimal place over 2 to the right. So just add 2 zeros everywhere. And now it will work out to whole numbers. Okay, don't worry. All right, so if I did it this way, we'll just take 99% of 100, which is 99 instead of the 0.99. People didn't like that. And here you get a 1 instead of the 0.01. All right, questions so far? And on your exam, and on your homework, I'll give you that total on the bottom, so you won't have to mess with worrying whether things come out to whole numbers, because some people don't like to work with decimals. All right, now, am I done? No, I have to, what have I used so far? I've used this piece of information, and I used what? This piece of information. Which piece of information do I still need to use here? This right here, 6%. Let's think about that. 6% of the time, Alyssa will incorrectly give a positive result. When? When you don't have AIDS. Where are the people who don't have AIDS? Right here. Of these, 6% are going to get positive. So 6%, be really careful. Please don't say 6% is 0.6 like that. It's not. That's 60%. It's 0.06. Okay, 6%. You have to move the decimal place over twice. 6% of the 9,900, these are the people who are going to get a false positive. And how many of them are there? 594. So 594 plus 9306 gives me 9900. They have to add up to that. And now what's left to do? We have to get our totals. And here we have to get 693. And everything adds up and we're good. So let's just see if we get the same thing as 1 out of 7 doing it this way. We'll just do it more exactly. And we'll just, here's how we did it intuitively. Intuitively. We're going to get something really close. And here's how we did it exactly. Exactly. Tell me what to write. What should I do? When someone, what's the chance that someone has AIDS given they tested positive? So what should be in the denominator? What number? Exactly. 6, 9, you look at all the positive people. Out of them, how many of them really have AIDS? Look up at this column. How many of these people really truly have AIDS? 99. Let's see, is that almost the same thing? Let me get my calculator out. Hope it works. Okay, let's see. So we want 99 divided by 693, and we get 0.1428, about 14%. Is that the same thing as 1 out of 7? 1 divided by 7. Whoa, look at that. Are you impressed? Are you impressed? I mean, it's slightly different because I round, this should really be 0.99. Remember? But I rounded it to a 1. So the point of this is that sometimes you don't have to go through all this exact, you'll lose your insight. Sometimes just imagine this example we did in class so you can keep this in mind, because it happens, if you can keep an intuitive example like that in your mind, it will stay with you forever. Whereas working out tables and stuff like this probably is too tedious. You're certainly not going to do it on the fly. Okay. Now, what's the chance that someone has the AIDS virus given the person tested negative? How are you going to do that? Where are you going to look? If they tested negative, what the denominator is going to be all the people who tested negative, and then how many of them really are infected? Do you see? That's a really tiny number. And we want that to be small, because if you test negative, you're just going to say, what's going to happen? Your blood is going to go into the blood supply. If you test negative, this is a screening test for blood. They'll take your blood and put it in into your blood supply, and it could potentially infect someone else. But that's a very, very small number. So it's extremely important to keep that small. It's okay if this number scares a lot of people. 6 out of 7 of them really don't have it. It's fine, as long as they're counseled. And each one of you who are counseled correctly, each one of you who are going into the medical profession should be aware of that. Don't scare these people. Say, look, chances are you don't have it. There's, majority of the people who test positive really don't. Just come back. We'll give you another test so that they don't freak out, okay? And then they'll come back, and of course, 6 out of 7 times they're not going to have it. Okay, thanks. Now, let's go to the next one, mammograms. And this is the one that inspired me to do these problems because, oh, you don't want another one. Mammograms are so depressing. Is that it? I heard this groaning. Mammograms, okay, have you ever had one? You should groan, they're not that much fun. It's like having your breast in two, squeezed, with two, refrigerator, inside of a refrigerator, 2 plates, just like. And the last time yeah? Oh, you had one? The last time go ahead. Can somebody, do a, telephone, tell me what she said? Will I do the calculations for the mammogram? Sure. You want me to? Yeah, I'll do them. Okay. What? You want me to only do decimals? Oh, without the... You don't want me to put whole numbers in? All right. No problem. Okay. All right, so that means if we're going to do decimals, we're going to start with 100. Is that what you're asking me to do, start with 100 no matter what? Sure, no problem. Okay, so you're going to help me out here? 100 no matter what. Okay, about 1% of the women who participate in routine screening have breast cancer. All right. Where are we going to put that 1%? That's going to be 1%, which is 0.01 of 100, which is what? 1% of 100 is 1, which means this is going to be what? How many don't have cancer? 99. All right, now, what's the next thing we want to do? So we've taken care of that. What's the 80% of the women with breast cancer, 80% of them will test positive. So where does that go? It's going to be 80% of what? 1, which is 0.8, which means what percent are negative? 0.2, because it has to add up to 1. Good. Now let's move on to our next one. What haven't we done? 10% of the women without breast cancer, where are they? 10% of the women without breast cancer, what happens to them? 10% of the 99, what happens to them? They falsely get a positive result, right? Isn't that what it says? 10% of the women, 10% don't have breast cancer. This is what happened to me, but I got the positive result. And no one told me that it was, you know, when the doctor called me up and says, you got a positive result, and it was actually a 90% effective mammogram, they told me. So they pretty much said 90% chance you have breast cancer, you probably have it, let's schedule you for surgery and so forth. And this was on a Friday. This is what got me inspired to do these problems with you all, and to look on the internet, and I found, and I want you to see this, that this question has been given to doctors in many studies, and only 15% of them answer correctly. Everybody looks at whatever this is and says, and mistakes. This says 80% of the women with breast cancer get a positive result. That's true. But they misread it to think that 80% of the positive results will have breast cancer. They think that the converse is true, and it's not. It depends very much on this number. Okay, so now I don't want to lose track, but we were right here, and we said 10% of the 99, like me, got a false positive. So you want to do it with 9, which leaves what? 89 point what? 1.1. All right, now what do? We want to add these up, and we get 89.3 here, and we get 10.7 there, correct? Didn't I do that right? Okay, so you can do it this way just as easily. Questions? All right, now let's think. If she gets, like me, a positive result, that's what happened to me, what's the chance? And I wish doctors would have told me this. What's the chance she really does have breast cancer? And instead of telling them this number, this 80%, this incredibly high chance, just simply do the statistics that we can do right here, and we look at all the people right here who get the positive results, and out of them, how many of them really have cancer? 0.8, which is percentage-wise what? What would that be? 8 divided by 107, or 0.8 divided, that's only a 7.5% chance, approximately. Not an 80% chance or an 85%, whatever. Also, what if she gets a negative result? What's the chance that that's wrong? That they say she's cancer-free, she goes merrily on her way, and she has a time bomb inside of her. What's the chance that that would happen? We want that to be really small, because she's not going to be retested. So if she gets a negative result, what's the chance? What's the chance she really has cancer and is just walking away blissfully without realizing it? What's the chance she really does still have cancer, even though it's saying negative? And thank goodness this is really small. What is it? Come on, you can do this. Out of all the people who get the negative results, that's 89.3, how many of those really have cancer? That's tiny, and that's good, because she's not going to come back to get retested, and these people always should come back, and when you come back, you can get reassured. So I'm not saying there's anything necessarily wrong with the test, I'm just saying those false positives, you have to realize that just because you get a positive result doesn't mean that you necessarily have cancer. Questions on that? And I'm not talking only with Brett, I'm talking about with all these diagnostic tests. Okay, now, birthday, that fellow, that green little guy with the helmet, it was his birthday tomorrow. Tomorrow's his birthday. March 1st. Okay, so what is the chance? Here's another counterintuitive problem. It's kind of fun to do. I don't know how much time I want to spend on this. I spent a lot of time on it last time because I bet the class that I would give everybody A pluses if nobody in like the middle section had, if there's no birthday match. And I said A pluses, I said we'd go out, we'd get drunk, we'd celebrate St. Patrick's Day, I'd be fired. But, it would just be all over for me because I can't just give everybody A pluses. So why did I do this? Do you think I was nuts? Do you think I was drunk? What happened? Let me explain. I just want to get your interest. The idea, this is a problem that says, we can do it as an eye clicker. What's the chance, so get out your eye clickers, we will. What's the chance that at least 2 people in this class, and let's say the class had 100 people, I don't want to make it really difficult. What's the chance that at least 2 people in this class share a birthday? All right, and so we thought about it, and people said, okay, how are we going to approach this problem? Intuitively, we thought. So somebody said, the first thing said, well, think about how many birthdays there are. And there's 365. And there's 100 people. So that was somebody's suggestion. And they said, so if you think that's the answer, but let's say, let's translate this into about a third. About, give or take some, about a third. That's the chance. What's the chance that 2 people, about 33% chance that there's a birthday match. Pretending you don't know there's not twins sitting here, or nothing like that. That everybody, nobody knows what people's birthdays are, okay? And then somebody else said they thought it was closer, bigger than that. Probably closer to, I wish I wrote these down. I did somewhere because people came up with them. I want to give the same ones to both classes. So I'm just going to write them down if I can find them. Exactly what I gave to the other class. What they thought it was. Okay, so here's this one. So A is about 33%. B was about a half. About a half. C was about 2/3. This is what people thought. D, and then I just said, let's do real extremes. Let's do less than 2% and greater than 98%. That's what we said. All right, so I want you, this is going to be your eye clicker class question, and I don't want you to calculate it or anything like that. It's hard to calculate. I just want you, we're going to do that together afterwards, but I want to see what your intuition says. Just like your gut level feeling. If you have 100 random people, what's the chance that at least 2 of them share a birthday? Okay? So, those are your choices, and I'm going to go to and here's what you said. So, let's look. A was what? About a third. I understand where you got that, but that seems likely, 1 out of, because it's about 100 over 365. Then B was about a half. C was about 2/3. Then the second most common answer was less than 2%. And then this was over 98%. People are still changing their answers here? Can you do that? I thought it was because I was clicking on it, Oh. Well, I'm glad I didn't tell you what the answer was here. Okay, so this was the most common answer, was less than a third. Just about everybody thinks it's less than a third. You either think it's less than a third or less than 2%. You think it's rare. You think it's pretty rare. Look at this, 26% of the class thinks. And together, what percent of the class? Over 2/3 of you, 16, almost 70% of you, think it's less than a third. All right, let's go back to the overhead. You're gonna think, only 20, so most of you think it's pretty rare, right? But I am willing to bet that it's not rare. I'm willing to risk my job because I'm going to give you every single person in here an A+ if I'm wrong. But I truly believe, and it's not because I know your birthday. I don't know anybody's birthday in here, but I believe there has to be, just because of, not has to be, but there's an extremely strong, way more than 98% chance that 2 of you must share a birthday. If there's 100 people, out of 100 random people, that the chance of 2 of them sharing a birthday is extremely high. So let's do it though. Let's see, how would we figure this out? And we really have enough information to figure it out. So what we want to figure out is the probability it's that at least 2 people in the class share a birthday. But remember that it's much easier to figure out not the opposite chance, but the complement chance. What do I mean by that? I mean that the probability of at least 1 match, which means 1 match, 2 matches, 3 matches, 4 matches, all the way up to 100 of you couldn't match, everything except the probability that nobody matches, that you all have different birthdays. There's no other possibilities. You either don't match at all, or there's at least 1 match, and that has to add up to 100% or 1. Okay? And so I'm going to figure out this. It's much easier to figure that out. And this, I say, is minute. Minute, which is why this is huge. Let's see if that's true. So, let's see. So how would we do this? We can start person by person, and let's see. And if you all have different birthdays, I'm going to go through this 100 people, and if you all have different birthdays, we can all just walk out of here, and whatever you want to do, I'll be fired. You'll all get A+. I'll probably be the first one to start unofficial. Let me in, Bar, come on. Oh, would I be, can you imagine what would happen to me? Unofficial, she does this, gives everybody, oh, I would certainly be a statistic. Okay, now, let's try it though. So, I want you each to write down your birthday, and please don't write down like, oh, January 1st, January 2nd, January 3rd, January 4th, and because then easily, it would only go up to 100 days, and there's 265 and days that wouldn't, you all have different birthdays. And I would be dead. So please be honest. And just write down your real birthday. Okay. So how are we going to start this? Well, what we're figuring out here is, and I just want to write it here, we're going to do the probability of at least 1, and I'm sure you've seen this a whole bunch of times by now, equals 1 minus the probability of none. But we're going to do none first because that's so much easier. So, what's the chance? The first person can have any birthday. You, for example, why don't you be the first person? Okay? You can have any birthday because you're not going to, I'm looking for different birthdays. Of course yours is going to be different. There's no one to match with yet. So out of the 365 days, you can have any. What is your birthday, by the way?
September 22nd.
September 22nd. All right, so we'll write September 20th. It's whose birthday? Are we done? Are we done before we started? Okay. Chance the second person. How about you? You be the second person. Now, she can have We're just looking to see if everybody has, what's the chance of everybody having different birthdays. And she can have any birthday but September 22nd. So the chance that she doesn't match one is out of the 365 birthdays. How many ways are for her to not match this? How many other days are there? So that's the chance that you don't match. That's overwhelmingly likely she's not going to match. What's your birthday? December 20th. It would be really weird if she did. Okay, now let's look at the chance person 3 doesn't match either these 2 birthdays. Right? The chance they don't. So how many are left? 363 out of the 365. That's the chance she doesn't match. So the chance of no birthdays so far means that all 3 things have to happen. So you multiply. Well, this is just 1, but I'll leave it in for form. And you multiply that. They all have to be different. And that's what it looks like. And that's overwhelmingly likely. It's very high chance. And what is your birthday? I mean, what is, oh, it was you. I'm so sorry. July 20th. So yes, she doesn't match. All right, and the 4th person. You be the 4th person. What's the chance you're not going to match? How many birthdays are left? You can't have these 3. How many birthdays are left? $365 minus 3 of those, so it's 362. That's the chance you're not going to match. And what is your birthday? January 12th. And you don't match. And the chance that the 4 people haven't matched so far is what? 365 times 364 times 363 times 362 over 365 to the what? 4th. All right, that's what we've got so far. Now let's just keep going. And I'm saying that pretty soon we're going to get a match. Really soon. Let's see if we do. And if we don't, if I go all the way up this aisle and we don't get a match, A pluses for every single person who's here today who answered the eye clicker. What? We've got a match?
My birthday's July 20th.
All right, we got a match. How many people matched some of these? Just raise your hand. How many people matched one of these already? Anybody? Somebody else in the back did, didn't they?
Hey, but it's unfair because that's a sample of more than 100 people.
Yeah, but look how far it would have taken us. By the time we got to her, would it have been more than 100? Do you think from up to here to her would have been more than 100? You see? Well, she saved you a lot of time. Yes, she did. All right, let's eliminate her then. Let's see. I bet it would still happen. We're not going to eliminate her. We're going to thank her. Now what you're saying, though, is you're up in the ante. You're saying that I have to have 2 matches because we already have 1. So 2. So I'm really putting myself out on the line here. Now I'm saying there has to be 2 matches. I didn't agree to this, but all right. I'll do it. All right, so we eliminate. So even if her birthday was something different, we're continuing on this journey. All right, so let's go. The next person, let's just do it. I'm going to start writing birthdays down so I just don't forget. Okay, so what do we have? January 12th. Who did I end up with? Who was the last person? What's your birthday?
September 10th.
September 10th. We're going to get one soon.
February 17th.
February 17th. Everybody pay attention. August 22nd or 27th? Okay. June 28th. No. There's the June 28th, right? All right, there's a June 28th. It's just gonna keep going. I mean, we'll see. Go ahead. Say out your birthday. June 28th. March 22nd. Anybody? March 22nd. Go ahead. 26th. That changes everything. Okay. September 29th.
August 1st.
August 1st.
April 30th.
April 30th. February 18th. 19th.
July 30th.
July 30th. You know, all these February people, I should be telling you happy birthday. You just had a birthday. Glenn?
I don't know when I was born.
You don't know when you were born?
No, I'm kidding. 15 August.
My grandmother doesn't know when she was born. What? 15 of what?
August.
I asked my grandma, she said, I don't know. We never celebrate birthdays. Okay. Say again? August 27th. July 12th. Okay, we've had haven't we had a match so far somewhere? No? July 12th. No, that's January 12th. Oh, go ahead. July 3rd. We had a match. Go ahead. November 12th. June 28th. Tell me, come on. There must have been one. March what? 19. March 19. November 30th. We should be getting one. January 10th. Yeah. February 10th. All these February birthdays. What? 1st of February.
August 31st.
Didn't we have an August 31st? No.
July 31st.
July 31st. We did. No, we had a July 30th. Okay, go ahead. November 2nd?
Good. November's too far away.
Go ahead. September 29th. That sounds so familiar. We had it. I have it. September 29th wins. Bingo. We got it. 2 September 29th. And look at that. Hey, guys. I know. Well, let me show you this. You didn't just miss out. First of all, let's just look how this works. Let's go to the PC. And if we just, where's a random birthday? Random birthday applet. All right, let's get rid of this. And here, watch. How many birthdays do you want? I'll just kept. Here come the birthdays. 50 of them. Let's see, there's a match. There's another one. There's another one. Okay, let's reset. If I do 100 birthdays, even if I only do 25, there's about a 50-50 chance. Let's see, with 25, let's see. It's about a 50-50 chance at 25. Yep. All right, let's do, here's what I bargained for was 100. Let me show you this. There's a 99.999. It's so counterintuitive. Ooh, wait a minute, I had to start over. Stop, reset, 100. Here we go with 100 birthdays. You'll see. In the last class though, we did 52 of them, or 53 of them or something before we got a match. And that's like, the chance of that happening is like only like 2%, and I was getting really scared. Really? I was thinking, you're lying, you're lying. But look at that. So the lesson from this is what? What's our intuition doing? Why are we so far off? And I think the reason in this particular problem we're so far off is because, let's go back to the overhead, and finish this first. Let me just finish to show you how to do this. In general, you all know that if you got to 366 people, you'd have to get a match, right? But let's say after the nth person, okay, what's the chance person n doesn't match anyone before him? Okay, so let's do this. So the chance that person n doesn't match anyone before him would be what? Out of the 365 birthdays, there would be what? 365 minus what? How many people were before him? N minus 1 people. So that's what we'd have to subtract off. We'd have to subtract off n minus 1 people, which is the same thing as what? 366 minus n over 365. All right, so that's the 300, that's after n people. So the probability of no matches in general after n people, you don't have to memorize this formula, I just want to show you what you'd do, is you'd say 365 times 364 times 363, all the way to the nth person who could not match the n minus 1 people ahead of him. And we said, you can write it this way or this way, 366 minus n over 365. They're all over 365, so that's 365 to the nth. And we know that as we get, the thing is, you know when you get all the way to 366, it's 0. But you get to almost 0 much faster. It's not a line. You're thinking it's a line. That, you know, you go 1/3 of the way to 100 people and you're, you know, you think it's a line and it's like 1/3 of your way to 0. No, you're almost at 0. It's a curve. So the choice, so in general, what do we want to do? The probability of no matches, okay. So what are we doing? The probability of no matches after what? 100, that's what we were doing, people is equal to what? 365 times 364, all the way down to 266, right? 366 minus 100. And it's going to be over 365 to the 100th. And if you do this, this is almost 0. It's not 0, but it's very, 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 very close to 0. It's like 0.000 something or other. Okay? Very close to 0. So the probability of at least one match is equal to 1 minus the probability of no matches. You either have no matches or you have one match. This is 0, so this has to be almost 100. So this is equal to almost 100. It's not quite. It's 99 point. Of course it's not 100. Theoretically, everybody could have a different birthday. You know, if you started at January 1st, you'd only get up to what? 1/3 of the year. But less than 1/3 of the year. But it's close. So it's not 100, I should say. It's equal to 99.99, I can't remember what it is, 97 or something. It's very close. All right, now why is our intuition so far off? I think our intuition's off is because I think each one of us hardly meets anybody who has the same birthday as us. We're not really thinking about those birthdays that other people have together. And that's a very different problem that is pretty rare. If we wanted to do that, how would we do it? What's the chance that out of the 100 people they share your particular birthday? So how would you do that? You would think, okay, pretend there are 100 people besides you or 99 besides you. I don't care. What?
100.
Okay, pretend in a class, pretend there are 100 people besides you in the class. We want to know, what's the chance that at least one other person has your birthday? What's the chance that at least one person has your birthday? And this is a much easier problem. Much easier. Think about it. Okay, so what are we going to do? We're going to say at least one. By now we know that's hard to figure out. So we're going to say it's the probability of at least one, because it could be 1, 2, 3, 4, whatever. At least one, this is going to be hard to figure out, equals 1 minus the probability that no one shares my birthday. I have a unique birthday. And that's going to be 1 minus what? Out of the 365 birthdays, what's the chance? We're trying to figure out the chance that no one shares my birthday. So let's start with me, December 1st. All right? What's the chance that nobody shares my birthday? I'll go to the first person. What's the chance he doesn't share my birthday? What's the chance his birthday is not December 1st? He could have any other birthday. What's the chance? 364 out of 365. Are you December 1st?
No.
I didn't think so. Not much of a chance of it. Okay, now I would multiply that by the next person. What's the chance? We should go to this side of the room. What's the chance that he doesn't have a birthday? What? Share my birthday.
363.
Be careful. 364. All we care about, I don't care if he matches that other person. All I care about is if he matches me. So what is it? He can have any birthday but December 1st. It's 364. And how about you?
Same thing.
Same thing. And how about you? Each one of you, all I'm interested in is whether you're at December 1st. I don't care if you match each other. So the chance that you don't share my birthday is 1 minus 3 over 64 to the 5th to the 100th. And that chance is pretty small. That's not anywhere near like 100% like this one. This is about 24%. Okay? I think we're done. I think we nailed that. I think we're done with this one. This equals 24%. You can do it on your calculator. About. All right, now, anybody have a birthday today? Oh, happy birthday. Let's all cheer for her. Anybody want to sing? Anybody have a birthday on February 29th that should have been tomorrow, but you just never get birthdays? Anybody in that situation? Really? So you're 4? 5? Are you going to be turning 5? Oh, we have a protege. And she doesn't even turn 5 this year. Maybe next year. I don't know when the leap year is. Okay, now let's go. And we have a lot to do now left. And I want to prepare you for the exam. So listen, I need an agreement here. We have 15 minutes left, correct? All right. Let's concentrate. These 15 minutes, if we all concentrate, will save you a lot of time. The homework's up. It's not hard. But everybody has to focus. Nobody can rustle around. Nobody can be distracting. Nobody leave. We've got an agreement? Do we? All right, let's do it. All right, so now we're going to be looking at something called the addition rule. The probability of one thing or another happening. But first, often it's helpful to list all the possible ways that an event can turn out. For example, 2 dice are rolled. What's the chance of getting a total of 4 spots, 7 spots, etc.? This will help you visualize all the possibilities. Imagine the first die you roll is a white die, and the second die you roll is a black die. And there's 6 different possible ways that the first can roll, and 6 different possible ways that the second die can roll. So there are 36 possibilities. Does everybody see that? 6 times 6 equals 36 possibilities. If you had a 4-sided die, it would be 4 by 4. Now, let's think the probability that the sum of the 2 die would be 4. Probability of getting a 4 on 2 dice. You can see it right here. Which ones add up to 4? There's a 3 and a 1, a 2 and a 2, and a 1 and a 3. So out of the 36, there's just think ways to get a 4. How many different ways are there? So you think, oh, 1 and a 3, 3 and a 1, and also 2 and a 2. Now don't write 2 and a 2 twice. 2 and a 2, it doesn't change anything. Here you have you could roll a 3 and then roll a 1, or you could roll a 1 and then a 3. 2 and a 2, you roll a 2 and then you roll a 2. They're the same thing. So this is just 3 ways. And you can do that with the other ones too. What else did I ask? The probability that the sum is 7. what would we do? You know it's out of 36, and all I want you to do is count the ways to get what? A 7. And you can see them along this diagonal. It's the most common thing, all of these ways. But you're not going to have this picture in front of you on the exam, so what are you going to do? You're going to think, 1 and 6, and then you'll have a partner, 6 and 1. I mean, the opposite. 2 and 5, and 5 and 2. And what else? Is there anything else? Yeah, 3 and 4 and 3. Is there anything else? No. So you have the 6 ways. And that's the most. It's across that diagonal. Now let's look at the probability that the sum of 8 with 2. Again, we have 36. And think ways to get an 8. And please, on every exam, I'm not kidding, somebody does this. I'm just writing it down. They go 1 and 7, 7 and 1. What's wrong with that? There's no 7 on the die. I mean, I swear, just don't do it. Don't do that, okay? Every exam, somebody does that. Okay, there's only 6 sides. So start 2 and 6, 6 and 2. And then you can think, what? 3 and 5, 5 and 3. And now don't make this mistake. 4 and 4, and somebody invariably writes 4 and 4 again. That's the same thing. Same thing. So there's only 5 ways. And you can see them. Look at them. There's these 5 ways. 6 and 2, 5 and 3, 4 and 4, 3 and 5. That's just one way. 1, 2, 3, 4, 5. Okay? Any questions on that? Let's move on then. Now let's go to the addition rule. Well, we've already done the multiplication rule. All right? You had to be a little bit careful. You had this, okay? But you had to be a little bit careful, because what if the probability of B changed depending on what happened here? Like, that would happen if you were drawing without replacement. But you handled that pretty well. Same now, and we saw, well, when you want both things to happen, you multiply, because the events get rarer. Like if you wanted to meet a good-looking guy and a rich guy, both those things, your chances are going to be lower. And if he fell in love with you too, that's going to make it even lower. And if he's in this class, that's going to make it even lower. When all these events both happen, your probabilities go down, you're multiplying. As opposed to the probability of meeting a good-looking guy or a rich guy, or a guy in this class, or a guy who loves you, or the guy next door, whatever. Then you have your chances increase. So you add chances. All right, so we understand when you have or, the chance that either or both of events happen, the chance that one or the other, or at least 2 of the events, one or both, that you want to add. That increases your chances. You want to add. But there's a little complication, just like there was here. And the little complication is don't double count. Like, what if you counted the good-looking guy as one guy and then he's also rich? That's the same person. You'd be double counting him. So you have to make sure that you're not double counting people. That if both of these can happen, don't count them twice. You have to subtract them off. That's all we're doing. So here's an example that will stick in your mind, that will illustrate this problem, I hope. By the way, it's called mutually exclusive if they can't both happen. Because, for example, here's an example. Here, the following 2 problems illustrate the difference between mutually exclusive and non-mutually exclusive events, and why these above formulas make sense, why these 2 formulas make sense. This is when they're mutually exclusive. This is when they're not mutually exclusive. What am I talking about? Here, pick a random person in this class. What's the chance the person is either the probability of male or female? We'll always start off, it's an or. You see or, so you're just going to say, okay, I'm going to add. plus the probability of female. Can I just stop there? Is this a case where it's mutually exclusive? If I'm a male, does that exclude the possibility that I'm a female? And if I'm a female, does that exclude the possibility that I'm male? Are they mutually exclusive? It means you can't be both. Mutually exclusive, because you can't be both. And please, this is not the time to argue about the PC stuff or whatever. Okay, mutually exclusive. You know what I'm talking about. I don't want to get into it. Not that I don't have sympathy and all. Okay, mutually exclusive because you can't be both. All right, you understand? As opposed to this. So that's fine. And in this class, if we did it, raise your hand if you're male. Just raise your hand high so I can see. Okay, 30% it looks like to me. So this is 70% and it adds up to 100 and we are fine. Now, what about this? What's the chance the person is either wearing jeans or female? Can I just stop right here and say the probability of jeans plus the probability of female? Do you think I can? What would happen? Raise your hand if you're wearing jeans. Whoa, a lot of people. Okay, that looked like about 40%. 50% maybe. Raise the hand, if your female was already 70%, we have 120%. That's insane. Can you get 120%? Can you? Yes or no?
No.
What am I doing wrong? I'm double counting somebody. Raise your hand if you're a female like me and wearing jeans. Raise your hand. Every single one of you were counted as part of this 50% and as part of that 70%. We double counted you. So we have to subtract off the probability of both. All right? And let's do that. So this was the 50%. This was the 70%. Now raise your hand if you're like me, a female. Do it again. Female wearing jeans. High so I can see. More. Come on, help me out. Okay. That looks to me like it's about 30%. So now we have 90% as our answer. And this is not mutually exclusive because you can be both. Do you understand the idea? I'm not going to have you worry about the language. I just want you to understand the idea. Now, let's turn the page. And here is the picture of it that might help you. This is not mutually exclusive. And if this is jeans and this is female, there's an overlap, right? This is both females who wear jeans. Where if this is mutually exclusive, you have male, you have female, and you can't be both. That's all I'm talking about. So let's do these problems. They're really easy. You can look at the language there, but let's just do this one first. These start off really easy because they're mutually exclusive. What's the chance of getting either a 5, the probability of a 5 or a 6 on one roll of a die? Well, that's just going to be the probability of a 5 plus the probability of 6 because you can't get both on one roll of a die. So it'll be 1 6 plus 1 6, and it's mutually exclusive. Same here. What's the chance of drawing from a full deck and getting either what? Either a heart or a spade. You can't get both on one card. So it's going to be the probability of a heart plus the probability of a spade. And that will be 13 out of 52 plus 13 out of 52, which is a half, or 26 out of 52. And they're mutually exclusive. Okay? Now, turn the page and we'll see something where we have to be careful. All right. If they're not mutually exclusive, these are not. Okay, and then you got to be careful. What's the chance of drawing from a full deck and getting either the probability of a heart or a queen. Do you see the problem here? You have the probability of a heart plus the probability of a queen, but look at the picture. You've got 13 hearts. You've got 4 queens. And right in here is who? Who's that? The queen of what? Of hearts. And she has to be subtracted off. So minus the probability of both. So what you would say is 13 out of 52 plus 4 queens out of 52, but you've counted the queen of hearts here and here. You've counted her twice, so you have to subtract her off. And then you get 16 out of 52. And our last problem, I know I'm rushing, so I'm going to stop right here. Questions for a second? For any questions? Okay, let's do the next one. The next one is, what's the chance of rolling a die twice and getting either a 5, the probability of a 5 on the first roll, or, do you see this or? So you just want to add right away, or you're adding the probability of what? A 6 on the second roll. Now you stop right there and you ask yourself, could I have both happen? Is it possible to get a 5 on the, roll the die, get a 5 on the first roll, pick it up, and get a 6 on the second? Is that possible? If it's possible, if both can happen, that means you've been double counting. So you have to say minus the probability of both. And they're called not mutually exclusive, which, all right, so what do? We say 1 out of 6 plus 1 out of 6 minus, what's the probability of both? Do you remember? Take it one at a time. The probability of getting a 5 on the first, both. And, what should I do here? And what symbol? How should I combine these two probabilities? I want them both to happen. What should I do with the right here? Raise your hand if you want me to multiply. Yeah. Multiply because you want them both to happen. All right? I want to show you this as a picture because you will understand it so much better. So let's just go back to this first page. And what are we doing? We're rolling, pretend the first die was white. The probability of a 5, we said it was 1 out of 6. There it is. And then we get 1 out of 5. Oh, shoot, 1 out of 6. All right? But it's all these right here. Our first is a 5. Our first is a 5. Then, or our second is a what? What's the problem say? Either your first is a 5 or your second is a what? 6. So on all these, either of these can happen. So here is the 1 out of 6, which another way of saying it is 6 out of 36. So 6 out of 36 have 5s on the first roll. And 6 out of 36 have 6s on the second roll. But do you see this one right here has been counted, double counted? Can everybody see that? Do you see how it's been double counted? It's been counted both as a 5 and a 6. So we have to subtract that off. So let's just see if it makes sense. Let's go back to our, back here. And when you see the picture, 1 out of 6, we can write it as 6 out of 36. We saw that had 5 on the first. And then we saw 6 out of 36 had 6 on the second. And then we saw there was one of them. There was one of them. The 5, 1, 2, 3, 4, 5, and the 1, 2, 1, 2, the 6. This particular combination, 5 on the first and 6, was double counted. It's one of these 6 and it's one of those 6. So we have to count. And our answer is going to be 11 out of 36. All right? Does that make sense to people? Now, in our last page here, you already know how to do these. The probability of at least one. So do you want me to just, and not all, do you want me to just post this on the, Because I think you've already done this already. Okay. Have a safe day tomorrow. Don't forget to do the survey. Also, don't forget to sign up for the conflict exam by tonight.